So good morning, everyone, or good afternoon, wherever you are. Hello, world, and welcome today to the virtual thematic workshop in mathematical sciences, nonlinear dynamical systems and delayed equations. This event is co-organized by the Academia Joven de Argentina, the TUAS regional partner for Latin America and the Caribbean, TUAS LACREP, and the TUAS Young Affiliates Network, TIAN. This event is also sponsored by the Brazilian Academy of Sciences and the Facultad de Ciencias Exactas y Naturales de la Universidad de Buenos Aires, the Faculty for Exact Sciences and Natural Sciences of the University of Buenos Aires. And I want to give special thanks to many of the people here being able to coordinate this event, especially to Franco Cabrerizzo, Jaqueline Mesquita, and Hernan Greco, who are behind controls. So to start the event of today, we will have some opening words by Professor Jin Lee, which I will present now. So Professor Jin Lee is in the Laboratory of Microbiomolecular Physiology and Metabolic Engineering from the Institute of Microbiology of the Chinese Academy of Sciences. Professor Jin Lee received his PhD in fermentation engineering at the Yangnan University in China in 2000. He has worked in the Wageningen Center for Food Science in the Netherlands and in the University College Cork in Ireland. In 2006, he was appointed professor by the Institute of Microbiology of the Chinese Academy of Sciences, and also in 2013, he was visiting professor in Cornell University. He and his research groups are interested in understanding the physiology of industrial fermentation from the molecular level and improving the performance of industrial microorganisms using synthetic biology and metabolic engineering approach. He and his team have received several awards, like the Chinese Petroleum and Chemical Industry Technology Invention Award, the Ministry of Education, Science and Technology Progress Award, and the National Science and Technology Progress Award. And Professor Lee is Director General of the Bureau of International Cooperation at the Chinese Academy of Sciences, and he's also the chair of TIAN. This being said, let me pass the word to Professor Ji Lee. Welcome, Professor.
Thank you very much, Ferran, for your very nice introduction. It is really my great pleasure to meet you, my dear colleagues, virtually, and to say a few words at the beginning of this virtual thematic workshop in math sciences. So first of all, I would like to congratulate the organizing committee for putting such a nice program in hand. And thank you for your hard work. And it is very important, and this very important and very difficult stage to keep our dialogue, communication in the scientific field going on. So I send my sincere congratulations and thanks to all your effort, all the effort that you have spent on. So I'm speaking here mostly on behalf of the TN, the TUAS Young Affiliate Network, which I serve as the chair, while Franco serves as one of the EC members. And Franco has been very active in promoting the TN's activity together with the TUAS LACREP and also the Argentina Young Academies and also Brazilian Academy of Sciences. So these has been very successful. So I would like to congratulate her on that, particularly since the foundation of the Argentina Young Academy. So you have organized many important events which bridges in different fields and also to burn the enthusiasm of many, not only young scientists, but also many excellent, outstanding scientists, representatives in this field. And today's event is just another symbol showing that we have such a passion for organizing that. So just a few more words on the TN. The TN is actually try to build up a network for connecting the outstanding young scientists, initially from the developing world, but hopefully from the whole world for that. So the TUAS Young affiliates are actually outstanding representatives from developing countries elected every year, 25 per person every year. So there are more than 300 towards young affiliates or alumni over the last more than 14 years also. So we actually try to build up a connection for those outstanding young scientists, and through them to build up connections more outstanding scientists. And so far, we have done very well because this network has been playing a very important role for organizing thematic workshop, which we see here. The virtual thematic workshop is also one of the forms that we have established. We also supported the travel in previous years to build up connection for people who do not know each other. But now we also try to use the TM money to support more scientists to use Zoom link, for instance, what we call it the internet infrastructure to support more thematic workshop virtually. So with these new forms or new what we call new normality, so we hope this kind of communication and dialogue for changing the knowledge, for exchanging knowledge and experience could go on, and it could help us to build up an even stronger connection. I'm also very happy to see that the basic infrastructure for the internet actually allows us to know each other even if we have not met before. This is a really great opportunity. So I think we could use more forms of this virtual thematic workshop to stick each other's interests together. Most importantly, what we don't want to just organize a workshop, we want to exchange some knowledge, but we also want to work together. And the boundary of science is the most important places where the new ideas and new outcomes to be generated. So I'm a microbiologist. If I have the opportunity to listen to the mathematicians, to the physicists, to the chemists, certainly a possible new idea, novel idea could be generated. I think you would agree with me that while we need to cross-talk at a different field, that's the essence of the scientific talking. Franco has been visiting me, staying in my lab for 2 months, but we also creating many ideas. I would also like to uh, invite you that if you are interested in visiting any of the institutes of the Chinese Academy of Sciences, you are more than welcome to contact me, and I will try to find out the best fit in your field and to connect you to those scientists. Chinese Academy of Sciences has more than 100 institutes, covering all the basic science fields. So I'm sure if you really look into detail of the program, you will find a program that you will be interested in. That's just a small advertisement at my stage. Last but not least, I thank all the speakers who agreed to speak at this event. I trust your seminar will be very encouraging and motivating. So I hope everybody could learn something from these webinars. And most importantly, I'd like to hear more from you. And if I can contribute anything in the future, please do let me know. Thank you very much. Great success to this event.
Thank you very much for these kind words, Professor Lee. Um, Now, I will give some generalities about the event of today before presenting our first speaker. So we will have 4 speakers, 2 keynote and 2 invited speakers. And just to remind everyone that is listening to us that you can send us the questions through the chat here in Zoom, or in the YouTube transmission, we will be taking note of these questions, and we will select the questions and send them to the speakers. The Q&A session will be from 12:30 to 12:50 in coordinated universal time -3. And well, this being said, let me introduce the first speaker of today. The first speaker of today is Professor Odo Diekmann. Odo Diekmann is an emeritus professor in applied mathematics at Utrecht University in the Netherlands. And he received his PhD from the University of Amsterdam in applied mathematics in 1974. His fields of interest are mathematical population dynamics, dynamical systems, and in particular, dynamical systems in infinite dimensional spaces. Professor Diekmann has held positions in the universities of Leiden, the University of Utrecht, and he has had visiting positions in the École Normale Supérieure in France, the Helsinki University, the Centre de Recerca Matematica in Catalonia, and the École des Hautes Études in Sciences Sociales in French, the Hokkaido University, Sapporo University, Fields Institute in Toronto, among others. Last but not least, Professor Diekmann is a foreign member of the Finnish Society of Science and Letters, and today he will give a talk in linearized instability principle for neutral FDEs in state-dependent delays. So I stop sharing now this presentation and pass the word to Professor Diekmann.
Yes, hello to everybody. And first of all, I would like to thank the organizers, and in particular, Jaqueline, who in my perception has been the driving force behind this meeting, for organizing the meeting and for inviting me. This is my first online presentation ever. And as I am an old-fashioned and low-tech person, this is a rather unexpected joy, and also, I must admit, a kind of a challenge. Anyhow, I have two topics to discuss. As you see announced, and I hope you see it all on the screen, this is about twin semigroups on the one hand and pseudospectral approximation on the other hand. So these are different topics, yet they are somehow related, because as we will see, they have to do with the choice of a state space and the idea that a delay equation is a rule for extending a function of time towards the future, so into the future, on the basis of the past, where the past is either known because you're already solving the equation for a while, or assumed to be known if you prescribe an initial condition. And then you extend this function by using the rule for extension, and then you define dynamics by shifting along the extended function, so by translation along the extended function. And as we will see, there are, on the one hand, this element of a rule for extension, on the other hand, this element of translation, and the properties are important when choosing the state space. But of course, ultimately, when you want to investigate the qualitative behavior or the quantitative behavior of particular systems of delay equations, you need to do computations. And so then also the issue of finite dimensional approximation comes into the picture. And that's where the two things kind of overlap. So the work on twin semigroups is joined with Stuart Verdun-Lunel, and he's actually also involved with the later work on the pseudospectral approximation, which originates mainly in Udine and in Trieste in Italy, and has more lately also involved Babette de Wolf, who is now a PhD student in Berlin. Please ignore the side remark in red on this slide, because this is recycling of an earlier presentation that I'm using here. There are two manuscripts on the archive, each for each topic, and they are both revised because they have been submitted to a journal and are now, the revised version is now considered by the journal. I hope so the main aim actually of my presentation is to get you interested in the contents, and so I hope you will go to the archive and download the manuscripts. And if you don't manage, please send me an email. I'm happy to send you the manuscript. So here on this screen, I show a delay differential equation where I have, to make my point, added a forcing term, f of t. So this equation involves 1 point delay, but also a function f of t that is a given function. And so apart from the initial condition, which is the phi of theta, that is prescribed on an interval of length 1, because the delay extends only 1 unit of time backwards in time. And proving the existence and uniqueness of a solution for this equation is very, very simple. As simple as proving it for ODEs, and sometimes even more simple if you can use the method as steps as here. But the the next issue is, what do we choose as the state space? So what properties do we choose for this function phi, the initial condition that you see here prescribed? And once we have made this choice, which I here indicate as the traditional and say most common choice, the continuous functions on this interval from -1 to 0 with values in R, we define dynamics by shifting along the solution. That is what is written in the next line, where x sub t means the function on an interval of length 1 preceding the time interval, the time point t. So it is a function of the variable theta, the bookkeeping variable in this past interval of length 1, and t is the current time point. And when you put f as 0, then the solution operators define a semigroup of operators on this space C. And this semigroup is actually strongly continuous, meaning that the orbits are continuous. And that's a very convenient property, because then there is a huge theory about delay equations. And in particular, one can easily calculate the generator, the infinitesimal generator of this semigroup of solution operators. And the action is just the derivative. And that means that this action only captures the aspects of translation, because quite in general, differentiation is the infinitesimal generator of translation. The rule for extension only shows up in the domain of definition of this operator A. And that's actually a nuisance. That's actually very bad and inconvenient, because it means that when we change the rule for extension, you have to deal with like an unbounded perturbation, because the domain of definition of this operator A changes and not the action. The action stays the same in this picture. And another way of noticing that exactly the same problem is to look at the variation of constants formula when you have this given forcing function f of t, of time, which end up here in this variation of constants formula, that you need to take into account that this forcing only applies in the point of extension, the current time point, and is not changing in any way the function in the history, because the history you just shift, you don't change it anymore. And that means that this function q that enters in this description by the variation of constants formula is the function that is 0 in the interval closed at -1, but open at 0, and then it jumps to 1 in the point 0. So it is discontinuous. So it does not belong to the state space X, to this space of continuous function. And that's another manifestation of the problem that I just noticed of the sensitivity of the domain of extension to the exact rule, the domain of definition of the generator to the exact rule of extension. Now, of course, you also immediately notice that an easy remedy is to say, oh, but Q is a bounded measurable function on this interval from -1 to 0. And well, we can easily extend these solution operators from the space X of continuous functions to the space Y of bounded measurable functions. And let's call to make a distinction, call the solution operators in this case, let's denote them by S of t rather than capital T of t, then we just extend them. That seems like the problem is solved. But the problem then shows up in quite a different way, because now we don't have any longer that this semigroup is strongly continuous. In particular, if you look at the map from T to S at T applied to a given phi as a map from R plus to the state space now Y, it's not continuous. And then you cannot define this integral in the variation of constants formula anymore as a Riemann integral. So now we solved one problem, but we got a different problem back. And usually then the solution is that people say, no, let's not try to extend the state space to the space Y of bounded measurable functions. Let instead get some other way of dealing with this difficulty of having this Q not an element in the space X. And so then you need to work with two spaces, or alternatively, you need to work with integrated semigroups. But the idea of twin semigroups is actually that we might perhaps address this difficulty of having to define the integral in a different way than in the standard way of having a Riemann integral for a Banach space valued function. And this different definition is really inspired by a very old paper, 1953, of Feller, who was, as you might know, very much interested in probability theory, where you have all kinds of semigroups of operators related to stochastic processes, and where also this issue of measurability is often an important issue. And Feller argued, well, why have abstract integrals? Why not, in what is called Gelfand-Petit's spirit, pair this element of the Banach space with an element of the dual space and have still this time dependence, and have that these orbits, I shouldn't say orbits, that these scalar valued functions that you get by this pairing, that they are measurable, and integrate those functions for a collection of elements of the dual space. Maybe not the entire dual space, but subspace of the dual space. And that is here indicated by Y diamond as a subspace of Y star, which is the dual space of the space Y. That was Feller's idea. And he had some informal and well, intuitive, or rather I should say stimulating remarks about it, but didn't really develop it into a theory. And not so long ago, Markus Kunze took this idea and elaborated on it, this idea of a Gelfand-Petit's integral. And he first of all said, let's be a little bit more specific of the properties of these two spaces Y and Y diamond. Let's make the assumption that this is a norming dual pair of spaces. Now, what does that mean? It means that each of the spaces is a subspace of the dual space of the other. So you have a pairing between the two that is continuous, as indicated by the first bullet on this slide. But secondly, let's assume that the discriminating power of the subspace is good enough to recover the norm. So in particular, the norm on the space Y is obtained by the supremum of pairing Y with all the elements of the unit ball in Y diamond, and vice versa, exactly the same property, but with the role of Y and Y diamond reversed. And that's a norming dual pair of spaces. And then the idea of Sjoerd Verdijn-Lunel and myself is to introduce on such a norming dual pair of spaces so-called twin operators. And twin operators essentially are, as the name indicates, two operators, one on Y and the other on Y diamond. And you might, in some sense, introduce the two of them in one go by saying, let's take a bilinear continuous map from Y diamond cross Y, the Cartesian product of the two times R, such that you have a continuity property, which I have not written. But in addition, that if you take one of the arguments Y and Y diamond as a variable and the other as, one of them fixed and the other as a variable, that you get continuity with respect to the weak topology that is induced by the other space. So the idea is that this norming dual pair of spaces is not just seen as Banach spaces, as two Banach spaces, but you really use the weak topology that each of the two spaces defines on the other. And you require that you have continuity with respect to this, this topology, this weak topology. And the point is that in that manner, the adjoint of one of, so if you consider L, for instance, as first as an operator from Y to Y, then its adjoint a priori just defines an operator on Y star. But when you have this the continuity that I require here, then actually you can take the restriction of this dual operator to Y diamond, and it maps into Y diamond. So you really have an operator also on Y diamond. And so in that sense, this twin operator is reminiscent of when you have a Banach space and it's dual, and you consider both the operator and its adjoint. So it's like a pair of the operator and its adjoint. Now, in general, when you have bilinear operators, you cannot take composition, but for this class of twin operators, you can, because you simply take, if you have the product of two operators, you let one of them act on one side first, the other on the other side, and then you take the pairing. And in this manner, you get a well-defined bilinear continuous operator as the product of the two. So you have a notion of composition, and therefore you can introduce a semigroup of operators, of twin operators, which is, as you see here, first of all, for each t, it is a twin operator. Then it has the familiar semigroup properties, that it's the identity when you take argument equal to 0, and it has this property that the addition of the real numbers is replaced by composition of the operators. Then we require, as part of the definition, an exponential estimate. In this case, you cannot, from the semigroup property, deduce this estimate, so you have to require it. And then in the spirit of Feller's account, we require that the scalar valued functions that you get by having both arguments at two sides. So I should also stress that also following again Feller, we use the notation that when we have the two arguments y and y tilde, or even if we have just y, sorry, not y tilde, y diamond, even if we have just y diamond, we write it at the left side, as you would do when ST would be a matrix. And that's really, in this series of twin operators, very convenient to write the arguments from the, say, dual space, the diamond space, at the left side rather than the right side, so just like in the case of matrices. So we require measurability of the scalar valued functions. And finally, the exponential estimate and the measurability guarantee that the Laplace transform is well defined, but we, as an extra condition, is well defined if the real part of the lambda is big enough. But as an extra condition, we require that this Laplace transform defines a twin operator. So again, an operator that can be defined both on Y and Y diamond. And starting from this, you can actually deal with such variation of constants formulas. And you need a little bit more than what I have just said. And that's, you need that this integral, which you get by having a pairing of every element in Y diamond with this ST applied to Q, and then this scalar function, given function f of tau as a multiplicative scalar factor. The integral is well defined, but we need that it really defines, and not just an element of the dual space of Y diamond, but really an element of Y. And then we need a little bit more to require, namely sequential completeness of Y when it's equipped with this weak topology induced by the Y diamond. What do we choose for Y diamond in the particular case of delayed differential equations? We choose the measures on the interval from 0 to 1, which we represent in the spirit of delay equations by normalized bounded variation functions. And then the pairing is as indicated here on the screen. And I haven't mentioned yet, but when I talk about delay equations, I always like to include, apart from delay differential equations, also renewal equations, because renewal equations are very popping up everywhere in population biology and also in mathematical epidemiology. And so we also have another type of rules for extending a function of time, where it's not the derivative that defines the rule, but rather the value of the function itself. That is in the case of renewal equations. And then the standard space to deal with renewal equations would be L1. But actually, in this twin approach to renewal equations, we would take the larger, so L1 we would interpret as absolutely continuous measures, and we would actually work with all the measures, so with the NBV functions. So the remarkable thing is that in the renewal equation case, we work with the same two spaces, but just the role is different. The true state space for renewal equations is the NBV functions, and the auxiliary space is the space of bounded measurable function. So concerning the twin semigroups, I leave it at this and invite you to look at the manuscript at the archive for more information. Like I said before, what I just described is theory, and oh yeah, I forgot to mention the motivation to develop this theory is that this twin semigroup business also extends to neutral functional differential equations, whereas the other ways of dealing with the difficulty that I mentioned about the domain of definition, etc., they have big problems with neutral equations. So that was our motivation. But it's theory. Whereas when you deal with concrete, say, population dynamical systems, you want to do, for instance, numerical bifurcation analysis. You want to study how the qualitative behavior of the system changes when you change parameters. And you want to do that in a systematic way. You can do a little bit with pencil and paper, but especially when you go all the way to periodic solutions, you get stuck and you have to use some tool, some numerical bifurcation tool. For ordinary differential equations, there are Auto and Modcond, and they are well tested and relatively easy to use. For delay differential equations, there are also tools like DDE-BIF tool, but they are for special classes of delay equations, like point delay equations, and certainly not for renewal equations. And my hope always has been that one day there would come also like special software that deals with more general classes of delay differential equations and also with renewal equations. But when I listened to talks by people from the Udine group, I realized that maybe there is a different way to get software that works for these systems. That is by approximating the delay systems in a systematic manner with finite dimensional systems and using then the ODE tools to deal with the finite dimensional systems. And that is the contents of the second topic. And to do this approximation, you work with polynomials on this interval from -1 to 0. And to define the interpolation points that you choose to introduce the polynomials, you first of all need to choose a mesh on this interval from -1 to 0. And in practice, we usually use the extrema Chebyshev mesh, but that's very convenient for implementation. But for the theory, actually, the zeros of Chebyshev functions are more easy to deal with. So there is a little bit of subtle issue of this choice of mesh points. But once you have the mesh points, you can introduce the Lagrange polynomials relative to these mesh points. They are defined by taking the value 1 in the point corresponding to the index. So when the theta I, the i's mesh point, is the argument, and you have the j's polynomial, then it's 0 if I is not equal to j, and 1 if it is equal to j. And so you have that when you sum all the polynomials, you get the function equal to 1, and that yields an identity for the derivatives, which I shall use later on. The approximation now is to say, okay, we have this function of time where we think of time in two ways. One is the time in the dynamical system sense, which is denoted by the t. And one is the time in the sense of a bookkeeping variable on this interval from -1 to 0, which is the zeta. And they always, in the infinite dimensional delay differential equation and renewal equation approach, enter into functions as t plus zeta. But for the approximation, we forget about this symmetry, in a sense, between t and zeta, and we say, let's approximate by a sum of these Lagrange polynomials with coefficients that depends on, and these are functions of the zeta variable, with coefficients that depend on the time variable. And now, since I have that on the left-hand side, when I differentiate with respect to t, I get the same as when I differentiate with respect to zeta, we require this property for the points numbered 1 to n. We require that when you differentiate the right-hand side here with respect to t as well as with respect to zeta, you get the same thing when you take the zeta, restrict the zeta to the point zeta k with k running from 1 to n. And that yields a system, a linear system of differential equations for the n factor C1 with component C1 to Cn. And it has a differentiation matrix, which is these polynomials of Lagrange differentiated and evaluated in the points. So you have two indices, one of the Lagrange polynomial and the other of the point in which you evaluate it, and that yields a matrix. And we use this property of the derivative that I indicated below in the lowest line on this slide to get rid, to also have this C not dependence in terms of this matrix D, but now applied to the factor of all ones. And so for the system of differential equations for this C, we have an n-dimensional system that is universal. It does not depend in any way on the rule for extension. And so it captures the translation, well, in an approximation. And the rule for extension is very easy to write down. It captures the dynamics of this zeros coefficient because that corresponds to the value in the point 0. So for the rule for extension, and you just use the equation to have that. And then you have an n+1 dimensional system of ODEs that you feed to the numerical bifurcation software for ODEs. And as a concrete example, I take the Nicholson's blowflies equation. The blowflies of Nicholson, they are the subject of an experiment that Nicholson, who was a British-born but Australian entomologist, somewhere in the 30s, he did relatively long experiments with blowflies that he gave limited amounts of food which they needed for baking eggs. And then he recorded the dynamics. And later on, Nisbet, Gurney, and Blythe took this simple point delay equation and showed that the dynamics recorded by Nicholson in the data and the dynamics that you get from this delay differential equation, that they are very, very close. So this is an example of a system of particular interest in population biology. And if we do a bifurcation analysis with two parameters, mu and beta, but for convenience, I have taken mu and beta over mu here as the two parameters. Then we have various regions in this two parameter plane corresponding to existence of a non-trivial steady state, and also the region of stability of this non-trivial steady state, and then it loses its stability by a Hopf bifurcation, and then oscillations arise. And here you see overlapping what you can do by the hand calculations for how you can derive these curves on the one end, and then when you feed this approximating ODE system into a numerical bifurcation tool, you see here the stability region that you get for n equal to 3. So for just 3 plus 1, so 4 points altogether in this interval from -1 to 0. And that's a remarkable feature of this pseudospectral approximation, that you can really get reasonable results, and in this case, even very good results, with a low number of points. So it's not a very high dimensional system. So it is a really extreme projection of the infinite dimensional system to a space of only 4 dimensions. So let me summarize the 2 topics. I have argued in the first part that in order to get a well-defined variation of constants formula for delay differential equations and for renewal equations, we might actually choose a large state space and sacrifice, therefore, the strong continuity of the solution operators, and yet define the integral by using this Gelfand-Petit type idea of having only the scalar valued functions that you get by pairing the state space element with an element of the dual space. And here you have to choose the space of the subspace of the dual space in a particular way, and then you can get this theory going. That was my first part. And in the second part, I argued that, okay, this infinite dimensional state space is bad for numerical bifurcation methods. Let's approximate by something that makes it finite dimensional. And here I've tried to argue that let's choose polynomials. Then we get a ODE system that really reflects, and you have to recall the ODE system where the part reflecting the translation really is independent of the particular rule for extension. So it's just the same as what we had when the action of the generator was just the derivative. So it only reflects so n of the n plus 1 equations reflect only the translation, and in the case of a scalar delay equation, of course, and the remaining 1 reflects the rule for extension. So it's really close to the structure that you have anyhow in delay equations. And then I hope you trust from what I showed in the picture, but I also invite you to look at the archive of a recent paper that we submitted, and where we show in more detail that you can actually prove that it has to perform well. So thank you very much for your attention, and this is what I wanted to say. Thank you.
Thank you very much, Professor Diekmann. It was a wonderful talk. I want to extend my apologies for giving the wrong title of your presentation. This is completely my mistake. And I remember the audience that there is a Q&A session at 12:30. You can send us your questions and then we will send them to the experts. So it is now my pleasure to introduce the second keynote speaker of this session. This is Professor Tibor Krisztin. So Professor Tibor Krisztin is a Hungarian mathematician working on dynamical systems and differential equations. And since 2000, he's a professor at the Bolyai Institute of the University of Szeged in Hungary, where he has also been the director from 2011 to 2014. Professor Krisztin studied mathematics at the University of Szeged in Hungary, where he obtained both his master's and PhD. And his research area is the theory of infinite dimensional dynamical systems, in particular the theory of delay differential equations. Delay differential equations appear in modeling of processes in biology, engineering, physics, economics, medicines, as well as social sciences. The wide and growing range of applications make this field interesting both from the applied and theoretical point of view. One of the main results of Professor Krisztin is a description of the fine geometrical structure of an infinite dimensional system generated by delay feedback system. He contributed also significantly to the geometric theory of differential equations with state-dependent delays. Last but not least, Professor Tibor Krisztin was elected a member of the Hungarian Academy of Sciences and received the R.E. Moore Prize for applications of interval analysis, and he was awarded Hungary's Cheney Prize in 2018. And today, Professor Krisztin will present the talk whose title is Construction of Periodic Orbits for Mackey-Glass equation. So with you, Professor Krisztin, welcome.
Thank you very much for this nice introduction. I'll try to share my talk. I don't know whether it works or not.
We can see your presentation.
Can you see it?
Yes.
Okay.
Maybe you want to make a full screen presentation.
Yes, but I don't know how to do it. When I share my file, I don't. So there is no. Wait. Usually it works with F file, but not in this case. Oh, is it okay?
Perfect. Thank you.
Good. So, good morning, good afternoon, or even good evening for everybody. And first of all, I would like to thank the organizers for the kind invitation to this online event, in particular to Jaqueline. It is my great pleasure to give a talk here. So my title is Construction of Periodic Orbits for the Mackey-Glass equation. And this is just the opposite of the previous talk. So this is a very simple looking equation and no, I mean, abstract theory behind that, but of course there are many results behind, the technicalities. Okay, so first of all, I would like to mention that this is a joint work with Ferenc Barta and Alexandra Wieg. They are former students of mine, and Ferenc did the computational work, the rigorous computational work of this of the results. So the outline of my talk is, first I just explain this Mackey-Glass equation, then I mention some basic earlier results, and then we consider the so-called limiting Mackey-Glass equation, and we construct stable periodic solutions. And then I will add some comments finally. So the Mackey-Glass equation looks like this. So this is a simple looking delay differential equation, and there are 4 parameters here: A, B, the delay tau, and n. All of them are positive. And this equation was introduced in 1977 by Michael Mackey and Leon Glass. And the equation modeled the feedback control of blood cells. And after that, there are other applications. And this equation is used to model many complex behavior of real-world phenomena. So first of all, we may assume tau is equal to 1 by rescaling the time, and then the Mackey-Glass nonlinearity appears here. This is the y divided by 1 plus y to the power n, and this is a so-called unimodal or hump function, and this creates a lot of interesting behavior in the equation. And I would like to mention that since 1977, this simple-looking equation attracted the attention of mathematicians working on nonlinear dynamics and functional differential equations. There are lots of results on this, rigorous mathematical results, numerical, and even experimental studies on this equation. And these results show that the dynamics is complicated. And so far, the dynamics is not fully understood. And probably the dynamics is well, for certain parameter values is very complicated. And one of the main goals studying this equation is to prove chaotic behavior for certain parameter values. Well, in this talk, we will not prove this, but at least we will show something about the complexity of the dynamics. So the Mackey-Glass nonlinearity looks like this function, this blue curve here, and the equation is this. So, and the phase space is the space of continuous functions on -1, 0 with positive values. And well, for each given initial function, there is a unique solution. And as usual for delayed differential equation, we give an initial function phi, and then we extend it as a continuous function, and we consider the segments. We restrict the solution to the interval t minus 1t, and we shift it back to the -1, 0. Then we will get this y sub t phi, and it will be in the phase space again. So formally, this is defined in such a way, and then the solutions define a continuous semi-flow. Now, some earlier results. So if A is greater than B in this equation, then it is quite elementary. So this is the situation for the nonlinearity f sub n, and this is A psi. Then all solutions go to 0, and this is quite elementary. So we assume that B is greater than A. Then it is possible to show that there is a non-empty compact global attractor in the phase space, and we are interested in the structure of this, because the structure of this A can give the long time behavior of all solutions. Well, there are some relatively simple cases. First of all, we can see that if we solve this equation, minus A psi plus B f sub n psi equals 0, then it has a unique positive solution, and then defines a constant solution, a stationary point of the semi-flow. So this is the intersection of these two curves. This straight line and this nonlinear function gives this stationary point. And it's possible to show that if n is large enough, then this is unstable. And then if we define xi1 as the maximum of the function, so it's here, then there is a result by Eduardo Liz and Gergely Röst and Jiang Wu, and they give conditions such that the global attractor contains functions which have values in this green region. And this means that then the long time behavior, the interesting part of the long time behavior, happens in a part where we have monotone nonlinearity. So in this region, the nonlinearity is monotone decreasing, and then there is a theory showing that in fact there is a Poincaré-Bendixson type result for these kind of equations. It was shown by Malépari and Sell, and this gives that the dynamics is relatively simple. In fact, no chaotic behavior, no complex behavior. And there is also, we can continue this, that we can define this xi2 such that fn xi2 is this value. And then on this interval, we have a so-called negative feedback property of the equation here. So if we are able to show that the global attractor contains functions with ranges in this interval, then we can show that we can apply the results for equations with negative feedback. But in fact, there are nice results for this case. And there is a Morse decomposition of the global attractor, and this was shown by John Malepari and McCord and Mishaikov. But there are examples with negative feedback such that even for equations with this property can have complicated dynamics. However, these results do not apply for the Mackey-Glass nonlinearity. They construct examples where this is the case, even very simple equations with negative feedback. Okay, now some numerical results. These results show that there are, well, complicated looking dynamics. One example is this: if A is this and B is this and N is large, then we have this type of solution. So this is the T axis, this is the X, and this is projected into the plane such that xt is here and xt minus 1 is on this axis. And then we get a curve on the plane. And somehow the shape of this projected curve, I mean, this gives whether the dynamics is complicated or not. Here is another example. So the shape of this projection looks quite complicated, and there are many papers, numerical papers, where people state that if they have this kind of picture, then probably the dynamics is chaotic or complicated. In this talk, I would like to show the following, that for some b greater than a and n large, there are stable periodic orbits with complicated structure. Well, complicated means that these projections are complicated. So this complicated is not a mathematical notion. This means that the projection of the solution, which is the orbit is in infinite dimensional phase space, and if we project it into the plane, then it looks complicated. And in particular, our results show that the above figures show stable periodic solutions. So for those solutions in the figures, these curves are simple closed curves in the infinite dimensional phase space. So in the right coordinate system, these solutions look like this. So this is it's a simple closed curve in C+, but if we consider the projections, then it can be quite complicated. Okay, so the aim is to show that the Mackey-Glass equation has this kind of complexity, that for some values of a and b, if n is large enough, then we have a complicated looking stable periodic orbit, orbitally asymptotically stable periodic orbit. So this is our Mackey-Glass equation with the parameters a, b, n. We rescale the time, so the delay is 1. And at the same time, we consider this limiting equation. So this f is just the limit of f sub n as n goes to infinity. And this gives this function. So this red one is the original f sub n, and this green one is the limit. So this is just psi here, 0 here. So it has a discontinuity at 1. And now the idea has a nice history. So if we usually, such an equation cannot be solved, I mean, explicitly. So one idea is the following: if g is a piecewise constant, for example, a step function, it is constant c on this interval, and xt minus 1 is in this interval for t is t in t1, t2. Then for x sub t, we have the following equation on this interval. This simply, so on this interval, g xt minus 1 will be just this constant. C. And this is a very simple equation. We can solve it. And then the idea is that these explicitly given exponential type solutions can give together a periodic solution. So by piecing together these nice looking functions, we can get an explicit solution of the ODE. And then, in fact, this means that we were able to reduce this infinite dimensional problem to a finite dimensional problem. And then somehow the strong attractivity property of this periodic solution gives that for nonlinearity sufficiently close to this step function, we still have a periodic orbit with this nice attracting property. This was successfully applied for several problems showing chaotic behavior for some simple equations such that the nonlinearity is close to a step function, and also to construct difficult type of periodic solutions for different type of equations. I would like to mention another paper where they had essentially the same idea we had, and so they considered this limiting Mackey-Glass nonlinearity for a different type of equation, and they constructed a simple-looking periodic orbit. So I will comment it later that by using their idea, we would get certain periodic orbits, what we obtained, but it's a very simple. But our aim is to construct more complicated periodic orbits. So I would like to remark that the construction of periodic solutions for the limiting Mackey-Glass equation is still an infinite dimensional problem. So it's because of this linear part here, of course, this is this zero makes it simple, but we have a linear equation here. And this means that, for example, if the range of the solution is here in 0, 1, then we have a linear delay differential equation, which is an infinite dimensional problem. And of course, the interesting thing happens when we have a solution which has values below 1 and above 1. Okay, so the nonlinear f is discontinuous, and then the existence and uniqueness of solutions is so it's not complicated, but we have to consider it in a different way as in the classical theory. So a continuous function is a solution of this limiting Mackey-Glass equation if instead of the differential equation, the integrated version of this holds for all tau and t with these properties. And so we introduce this subset of the phase space. So we consider functions on -1, 0 with positive values, but such that this function takes any value only a finite number of times. So the inverse image of any C is finite. And well, we are able to show that for each initial function from this set, there is a unique solution such that all segments belong to this set. So this is invariant under the solutions of this limiting Mackey-Glass equation. And also so the reason to consider this subset is that somehow we have a difficulty when we consider solutions crossing 1. And somehow we would like to guarantee that we have only a finite number of crossings. And in fact, we would like to control the crossings. It will be clear how. So if you have a solution of this limiting equation, then we say that this has this property if essentially this means that if the solution is close to 1, then the set of those times such that this is close to 1 can be controlled by constant times this delta. And then the proposition says that if we have a t-periodic solution of this limiting Mackey-Glass equation such that the initial segment is in this subset, and for the solution we have this, that each time when the p of t is 1, pt minus 1 is different from a over b. This a over b comes from the fact if this p of t is 1, then the derivative cannot be close to 0. So this is different from 0. So this means that somehow the periodic solution crosses 1. So then it is possible to show that this periodic solution has this property, this regularity property. And now we construct stable periodic solutions in the following way. So first of all, we assume the following. So we have certain values b, a, such that the limiting Mackey-Glass equation has a periodic solution with minimal period capital T, such that this solution is greater than 1 on the interval -1, 0, 0 at 1. And we have this property pt, p times t minus 1 is different from 1 a over b for all t. In fact, this means that if p of t is 1, then pt minus 1 cannot be a over b. So this is exactly the same condition as we had before, guaranteeing that the solution crosses 1 in a regular way. Then we have the following theorem. Under this assumption, if n is large enough, then so the assumption is for the limiting equation, and if n is large enough, then for the classical Mackey-Glass equation, we have also an orbitally asymptotically stable periodic orbit with minimal period Tn, such that this periodic solution or this periodic orbit tends to this periodic or solution of the limiting equation, and the same for the periods. So of course, so first of all, we have to prove this, but first we have to find values b, a, such that this is true. So we have this kind of periodic solution for the limiting Mackey-Glass equation. How to find a, b, and p for the limiting equation? So first of all, we have analytic proofs. One simple case is when b is large enough comparing to a, and I just show, for example, if a is 2, b is 15, then we have this kind of periodic solution. And if we project this, so this xt is here, xt minus 1 is here, then we have a closed curve. So it is possible to prove this by hand. And there is another case, and this is the case when b is close enough to a. So for each fixed a, if b is close enough to a, then this equation has a periodic solution with this p epsilon with minimal period capital T epsilon, and this tends to infinity as epsilon tends to infinity, this 0, sorry. So this is then we get equations something like this. So, and the projection looks like this. And in fact, this is nothing else than, well, below 1, we have a linear equation. So this is nothing else than we have to consider the behavior of a linear equation with a very particular initial function. And then somehow we have to guarantee that when it crosses 1, it remains above 1 for an interval of length greater than 1. Then we have such a periodic solution. Okay, and then we have rigorous computer-assisted proofs for the more interesting cases. So first of all, by a non-rigorous numerical technique, we find A, B, and the solution such that the initial segment is this in this set. So this is just above 1, and the solution starting from this phi leaves this set for some time, and later it returns to this set. And then once we found such a P, such a periodic, so it is possible to show that this is periodic, then we can use rigorous numerical tools to prove the existence of A, B, and P. So first of all, the discontinuity causes difficulties because we have to check the crossings of 1, and it means that we have a series of Poincaré maps, and usually for rigorous numerical results, computing the Poincaré maps, increasing the inaccuracy. So this means that the errors increase by an exponential rate. So there is a new idea here. So the new idea here is that the solution segments for this particular Mackey-Glass nonlinearity can be explicitly constructed within a set of functions, within the following set of functions. So this is exponential and polynomial. And we have pieces of the solution, and all the pieces have these type of structures, and then it helps a lot to to prove rigorously that we obtain such a periodic solutions which satisfies that assumption. We need to extend then the results to the classical Mackey-Glass equations for relatively large n. Before saying something about the proof, so first of all, we have to prove this theorem under this assumption. Then the rigorous numerical technique verifies this assumption. But also the proof of this theorem is not straightforward, because essentially it shows that for this discontinuous limiting Mackey-Glass equation, if we have a certain periodic solution, then, well, for the perturbed version of this Mackey-Glass equation, we still have a periodic solution in a close to this original periodic solution. So this is a kind of perturbation result. And in order to be able to do this, we need this kind of regularity property of this periodic solution. So first, I just show examples where this technique worked. So at the beginning, I showed a complicated looking solution, for example, this, and it's possible to show that, so it starts, so this is 0, it starts above 1 here, so the segment is above 1 here, and it is 1 at 0, and then we extend it somehow and find somewhere that here it is again, the value is 1, and so if this would be capital T, and capital T minus 1 is somewhere here, and it is above 1 on this interval of length greater than 1. Of course, we have several intersections, crossings with 1, and well, we have to show this regularity property of this solution, and it comes from the fact that the nonlinearity is 0 if for xi greater than 1, that if we just put this function back here to 0, 1, and then it defines automatically a periodic solution. And then the projected version of this looks like this. This is for the limiting case. For large n, the picture is quite similar. And there is another example, and here the idea is the same. We start a solution. The initial function is arbitrarily on -1, 0 here, just it is above 1, and at 0 the value is 1. And then we get this solution, so it crosses 1 several times, and somewhere we find that that we will have a minimal period close to 20, and these green things mean that so we, of course, when this interval arithmetics is applied here, then we show for a larger region that it is above 1, or or below 1, or the derivative is non-zero when we are close to 1. And the projection of this looks like this. So this is a numerical result, but this is a rigorous numerical result. It is verified by interval arithmetics. So in order to prove the theorem, which says that once we found by using this type of periodic solutions for the limiting equation, then for the original equation for large n, we still have a periodic orbit close to the periodic orbit of the limiting equation. And the key property of the nonlinearity, or of the Mackey-Glass nonlinearity, is the following. So this is f sub n, xi divided by 1 plus xi to the n. So this looks like this for large n. And the green one is the limit. So the derivative, if we fix a gamma, which is small, then the derivative for xi between 0 and 1 minus gamma even for all, for all xi, this is true. So for up to 1 plus gamma, this is n over 4, the derivative. And if xi is greater than 1 plus gamma, then we have this kind of estimation. So somehow the key is that as n goes to infinity, this goes to 0 exponentially, while this estimation is polynomial. And it is not difficult to give examples where we have the limiting shape of a nonlinearity is this, but f sub n doesn't satisfy these type of estimations, and then we are unable to prove this theorem. So this simply means that the derivative is relatively small up to this value, and after that, if n goes to infinity, the derivative, the absolute value, goes to 0 exponentially uniformly for xi in 1 plus gamma infinity. So, and the proof is the following. So we assume that m is an integer, and we have a solution with this regularity property. So this means that the crossings are crossings of 1. These are somehow regular. So the solution spends relatively little time at 1, such that the value is 1, is close to 1. And then we are able to to give explicitly constants so that we can prove the following. If we have a solution, X is a solution of the limiting equation with this nice crossing property, and we have another solution for the classical Mackey-Glass equation, and they are close to each other, the initial functions, then for large n, they will be close to each other for a fixed time interval. So this is a kind of continuous dependence, but now we compare two solutions, but one is a solution of the limiting equation, the other one is a solution of the other equation with n is finite, but n is large. And in order to have this, to control this difference, we need this regularity property expressed by crossing one in a controllable way. So now we assume that we found a periodic solution with minimal period capital T with this property. So we found this either by using an analytic tool or by using a rigorous numerical tool. So for example, we have this. So we have a periodic solution, something like this. And we also have this property which guarantees this regularity of the periodic solution. And then we do the following. So we just shift this period. So this takes the value 1 at 0. So we just, but it is greater than 1 on an interval such that its length is greater than 1. So we can shift this solution such that it is above 1 plus gamma for some gamma, and it takes the value 1 plus gamma at 0 and also at the period capital T. So this is the shifted version is just Q. And then the reason is that when we have the initial segment looks like this, and also at capital T it looks like this, and we define this subset such that psi is in this function space. It is the psi 0 is 1 plus gamma, and it is above 1 plus gamma for all values of S from this interval. And then the real role of gamma, we have a space for perturbation. So we need functions above 1. And then we have the following. We are able to show the following. And this is also very important if we have an initial function from this set, and we consider the initial function, this segment Q of sub 0. This is also in this set. Then on the interval 0, 1, the difference is small. And this is, of course, this Q is this given periodic, the segment of this given periodic solution, but psi can be arbitrary. It takes the value 1 plus gamma here, but it can be any function here. But still we have this. And the reason is that if the value of the function is above 1, here it is above 1 plus gamma, then it is very small. And for the limiting equation, it is 0. And then we can apply the continuous dependence results to prove that the difference between these two solutions is small. And then this allows to show that this solution, so this is Q is the solution, periodic solution of the limiting equation, and Y is the solution of the equation with the classical Mackey-Glass equation. Then we can guarantee that Y and Q remain close to each other, and then it guarantees the existence of a return map. So if we start a solution from this set, it will return to this set after some time tau. So, and this return map, of course, if we have a fixed point of this return map, then this guarantees a periodic solution, periodic orbit. And our claim is that this is a contraction on some subset of this S sub gamma. And as I mentioned, these conditions play a role in the estimations, and well, the estimation looks like this. We have this function a sub n, and these are, all of these are constants, suitably chosen constants, and a sub n looks like this. And capital N is related to the length of the period, yes. And then this means that, so everything is constant here, and if n goes to infinity, then this a sub n goes to 0, so we can guarantee that this coefficient will be less than 1. That is, this is a contraction. And once this is a contraction, then it has a fixed point, and then it means a periodic solution close to P. And then we also can prove orbital stability of the obtained periodic orbit. And that is an easy consequence of this, this contraction property. Okay, so then finally, I have some remarks. First of all, okay, we are able to get complicated looking stable periodic orbits for certain values B and A. But this doesn't mean that we can find it for any B and A. So we have to find B and A with this property. But for other values of B and A, we were unable to find this, and probably such a stable periodic orbit doesn't exist. So, and also a remark that the existence of this stable periodic orbit doesn't mean that the dynamics is simple, but numerical results show or suggest that in many cases, the dynamics is probably simple, but there is no proof for this. So we only know that this periodic orbit attracts a small neighborhood of it. And also, if there is a stable periodic orbit of this type that we constructed, then there is a connecting orbit from 0 to the periodic orbit. So the alpha limit set, it would be 0 of that orbit, and the omega limit set of the constructed periodic orbit. And the technique works also for other equations. For example, it is interesting this version of the Mackey-Glass equation where we have y squared here, and this equation was used to model LA effects, and well, we have results also for this, and well, it's also homoclinic orbits, and for this there is a hope to prove chaotic behavior, but it's different from the original Mackey-Glass equation. So, well, this is the end. Thank you very much for your attention.
Thank you very much, Professor Tibor Krisztin, for this wonderful talk. I would like to remind the audience that you can send us your questions for the question and answer session that we will have at 12:30. This being said, it is my pleasure to introduce the next speaker of today. The next speaker of today is Professor Jaqueline Godoy Mesquita. And Professor Godoy Mesquita completed her PhD in mathematics in 2012 at the University of Sao Paulo, with a period of stay at the Academy of Science in the Czech Republic in Prague. She has held 2 positions as postdoc in the University of Santiago de Chile and the University of Sao Paulo, and she holds the position of professor at the University of Sao Paulo from 2013 to 2015, and is currently professor at the University of Brasilia since 2015. Professor Godoy Mesquita has won several awards, including the International Bernd Albach Prize for Students. She was also elected to participate at the 5th Heidelberg Laureate Forum in 2010 and to participate in the Oberwolfach-Leibniz Fellow in Germany. Professor Godoy Mesquita was elected a young affiliate member of the World Academy of Sciences from 2018 to 2022. She's an affiliated member of the Brazilian Academy of Sciences and regional secretary of the Brazilian Mathematical Society. She was the Capes Alexander von Humboldt Fellow at the Justus Liebig Universität Gießen in Germany, under the supervision of Bernhard Leini-Weida and Hans Otto Walter. In 2019, Professor Godoy Mesquita won the Prize for Women in Sciences award by L'Oréal, UNESCO, and the Brazilian Academy of Science in the category of mathematics. And today, Professor Godoy Mesquita will present a talk whose title is Linearized Instability Principle for Neutral FDEs with state-dependent delays. This being said, welcome, Professor Jaqueline Mesquita.
Thank you very much, Ferran, for this introduction. I will share the screen, just a second. Can you see?
Perfect.
Okay, so
Wonderful.
Okay, thank you very much. So thanks for the introduction. It's a great pleasure to me to be here and to talk in this event. And today I will talk about this linearized instability principle for neutral differential equations with state-dependent delays. And this research was developed last year when I was as Humboldt Fellow at Justus Liebig University, so it has the support of CAPES and the Humboldt Foundation. And the outline of my talk, I will share in two parts. I will start with some motivation, why to study this type of problem, what's the motivation behind of that. And then I will talk a little about this linearized instability principle. The second part will be a little technical. I will show a little about the techniques to prove the result. And the first one will be a type of motivation. So just for people that are not usual with delay equations, as Professor Odo Diekmann and also Tibor Krisztin mentioned, these types of equations are very important to model many things. So it's many phenomena like a population model, as Odo Diekmann mentioned. Also, you can have many types of famous equations. And here in my work, I'm very interested in equations which involves state-dependent delays that also have a lot of applications. So it was started with some motivations from the driver's work to study about the body problems in electrodynamics. However, there are a lot of applications of these types of equations. And for that, I also recommend a chapter of book from Hartung, also Krisztin, and Hans Otto Walter and Wu, that they bring a lot of applications of these types of equations. And my work was made in collaboration with Professor Dr. Bernhard Leini-Weida from Justus Liebig University in Germany. And the timeline of my problem, the motivation, so it started, the model was introduced for the first time for Brunovsky, Erdely, and Hans Otto Walter in 2004. And they had this type of model here in order to study about currency exchange. And here they considering this with this constant delay. And then later, Hans-Otto Walter, he studied more about this problem and proved some properties concerning bifurcation and the periodic solutions of this problem. And then we have some contributions from Garabi, Kovacs, and Krisztin also for that model to investigate it about asymptotic behavior of the solutions. And then in 2012, we have that Stump was the first one to reformulate this type of problem, considering not only constant delays here, but the state-dependent delays. So here you can see the delay depends on the state. So Stump was the first one to formulate this model in such a way. Then later we have that Hans-Otto Walter, he improved that model and he considered, instead of this type of model, a neutral type of model. So we have now a neutral differential equations with state-dependent delays. So here is the formulation that Hans-Otto Walter brought, and he gave an interpretation about this currency exchange to considering in this type. And then Hans-Otto Walter, he proved a lot properties concerning this equation. So he proved the existence of SEM flows, also differentiability of solutions, also the linearized instability principle for these equations. However, one open problem was about the linearized instability principle for this type of equations. And one of the most difficulties in order to have a linearized instability principle for this type of equation is because when we look for the spectrum, when we deal with neutral, it could be very hard because we can have infinite eigenvalues in the spectrum, and it turns very hard to have some lower estimate for our semigroup. So that's why it was so hard to have this type of principle of linearized instability. However, in our case, we found out that we could have some examples that we can have a lower estimate for our semigroup. So we used that, and the main idea behind was to use the invariance of the const. So the problem, as I mentioned before, is this one here that you can see, and the main motivation is about the currency exchange. And our idea is to try to rewrite that problem in an abstract form. So we would like to rewrite that in that abstract form, and we would like that this G satisfies certain conditions in order to ensure that the SEM flow, the existence of SEM flows, also the differentiability of the solutions, and some properties concerning our spaces and our solution in order to prove our results. So here is the way that we would like to rewrite our equation. So here we have this type of equation, and then we will use these two types of evaluation maps. So here's the evaluation map, and here we have this restriction of the evaluation map, and use then we will rewrite in this form using the following. So if we define our G, as we can see here, using these evaluation maps and also the projections, we can have that, we can rewrite that problem in that abstract form. And Hans-Otto Walter showed that defining the G like that, we can have some properties that will be very important to us. I will show then. And with that, we can ensure many properties concerning our problem. And so now we would only deal with this abstract form of the problem. And first, I will define what the solution means. So we say that a continuous differentiable function is called the solution of this problem if satisfies the problem for all t here. And also if you have that this one belongs to W if t belongs to this interval. So then we have our assumptions. So the first one is about the continuity of our G. So we ask about the continuity. The second one is about the delay term, and the neutral term never vanishes, which means that here, if you see, we could have that our functions, if they are equal in the interval, except in the part of the zero, like in minus delta and zero, we don't know how it looks like. and if it's not during that time, so it does not influence our G. So our G is equal independently what happens with these two functions in minus delta to 0. So we only matters what happens here, and then we have that our G will have the same value. So it will be very important to us in order to have some properties. Also about some local estimated for G. So we have these types of estimated. Also this one that will be very important about the linear extension of the derivative. So every derivative has this linear extension, so we can extend it for this space. And using that, we can have that D set that's defined this way, if no empty, is a continuously differential submanifold of the Banach space C2 of the twice continuous differentiable functions with this norm here. And it will be very important to our proposal here. Also, we have more estimated concerning our G. And here also about the upper semi-continuity. And again, other type of estimated. So with all of that, we also can consider this closed subset given by this. And this closed subset is a closed subset of our manifold. And it has the property of the invariance, which means that Hanzoto-Walter proved that if you start in that set, so you continue in that set. So we have this invariance, which will be very important to us here. So our goal is to prove that 0 is unstable, and we will use the invariance of the cone for that. So the assumption that we will start with the abstract assumptions, and then we will come to our concrete problem. So we have here our assumptions. So here we have that we can decompose our space in the unstable part and in the stable part. And we have that this is the estimate for our semigroup, the unstable part, and here related with the stable part. Also here we have the assumption about our SEM flow. And also we have that if we define this R as this difference here, so assume that there exists T1 bigger than 0, such that for every epsilon there exists delta for all x in that ball, such that T1 belongs to this interval, and we have this estimate. And so since we don't want to all the time deal with that constant K that appears in the assumption A1, we will work here with the equivalent norm that we denoted by this, and then we can take our K equal 1. So we have this estimated here for that, and then also we have this other definition. Oh, sorry, for, oh, I don't know how to, okay. So we have this estimated here for our norm. So here we have that, okay. So here we have the definition of our cone. So here we have the elements of the cone, such that we have that V is the stable part and U is the unstable part. And also we have here these estimates. So with that, we have this lemma here that has that if you take C here in that interval and T1 bigger than 0 in the same way as we had in the assumption A3. So if you take this K like this, and here we have that this K is bigger than 1 by the definition. So we have that there exists a delta such that if we start in the cone, so we have the T1 map continues in the cone. So we have the invariance of the cone. So we start in the cone and then the T1 map is still in the cone. And more than that, we have the expansion of the unstable part. So we have here that the unstable part expands. So let's see now a schedule of the proof. So here we take this epsilon, like this minimum here, and delta as in A3. And then using these facts about the projection. So we have here the projection for the unstable part of the T1 map. And then we have that we can rewrite like that by the definition that we had before for this R. And then using the triangular inequality for the other side. and also the estimated concerning the semigroup in the unstable parts, and also the estimated concerning this R, we have that here. And then here using the property of the cone, so we have this other estimates. Also here concerning the unstable part, we have, again, by the definition of R, we can rewrite like that. And then using again the triangular inequality and using the estimated for the stable part, and also here the assumption A3, we have these estimated here, and using the property concerning the projection, now we have this. So we have this other estimate. So now, by the definition of this norm, we have that this one is the maximum between the stable part and the unstable part, but this one we saw that is smaller or equal this one here. So we have that this one is smaller or equal the maximum between these two quantities here. So if this maximum is equal this one here, so we have that this is bigger or equal this because of this maximum here. And if we have that C is smaller or equal 1, we have that this one is bigger or equal C times this. So it shows that our T1 map belongs to the cone in that case, in the case that the maximum is equal this one here. So in the other case, in the case that we have that the maximum of this is this other part here, so we have that now we use this here, and then we have this estimated concerning this, and then sum and subtracting this other term here, we have this equality, and then using the choice of epsilon, we have this other inequality here, and using the property concerning the our T1 map, the unstable part of the T1 map that we saw in the beginning, we have this other estimate. So we have, again, in that case, that the T1 map belongs to the cone. So we showed the invariance of the cone, and now it remains to show the expansion of the cone, the unstable part. So here we have this one here again, by what we saw before, the estimates, we have that. And here using the fact that X belongs to the cone, so we can rewrite this other part here. And using the choice of the epsilon, we have this other estimate here. And making the calculations, we have this equality. And here, if you see, this is exactly our Q that we defined before. So we have that this inequality, and we show that the unstable part expands. So we can show also the expansion of the unstable part. So we proved this for the abstract framework, and then when we pass for the concrete framework for our case, the E can be translated by C0, E2 can be translated by C2, X can be translated by XG2 star, and S of T equal S of T. And also we can prove that in our specific case, under the conditions concerning G, the G0 until G7, we have that all the conditions A1, A2, and A3 are satisfied for our concrete case. So we can apply our invariance of the cone for our specific case. And so here we needed this more additional hypothesis concerning this derivative that has a continuous extension. And using that, we can define this manifolds that will be equal xg2 star that we saw before, that closed set of the other manifold that we saw before, that's invariance. And here, if you intersect that with C3, we have that this M3 is a submanifold. And then using that, we have all the ingredients to have our principle of linearized instability. So the main idea behind that is the following. So you start in the ball, and you start in the cone, and also in the M3, and then you apply the T1 map. If you are still in the ball, so you need to continue. So if you are still in the ball, you need to do again. So you will be in the cone because the cone is invariant. You are not maybe in the M3 because M3 is not invariant, the manifold, but you are in the X2G star because this one you know that's invariant. And then you can apply again the T1 map, And at some moment, you should escape from the ball because we know that the cone expands the unstable part. So if you do not escape, you apply again, but in some moment, you need to escape from the ball because of this property of the expansion of the cone. And so with that, we have the property concerning the linearized instability principle. So we assume that condition, and then we have that there exists Tn bigger than 0, such that in some moment you will escape from the ball, and then we have this instability. So now I would like to talk about some more open and developing problems in that sense. So we proved that about the linearized instability, and now we are trying to improve about the linearized instability to have like some exponential estimates, to have a more general estimates for that. And also other thing that's still open is about periodic solution for these types of equations. And the other class of equations that I am interested is about measure neutral functional differential equations with state-dependent delays that are more general than this class. And you can put inside of them impulsive equations and neutral equations involving impulses, also involving like discrete parts. So types of dynamic equation time scales inside of this one. So I am interested about this class of equations, and also other open question that we have in that sense. It's about attractors for neutral functional differential equations with state-dependent delays. We started to try to discuss about these, but we haven't, we didn't evaluate a lot in that sense, but it's some open problem that we are interested about how it should be the attractors for these types of equations. So that's it. Thank you very much for your attention.
Thank you very much, Professor, for this wonderful talk. I want to thank you again and remind the audience that you can send your questions through the chat in Zoom or our stream in YouTube. This being said, it is my pleasure to introduce the last speaker of today. It's Professor Guilherme Mazanti. Professor Guilherme Mazanti has a degree on electrical and electronic engineer from the University of Sao Paulo, and also an engineering degree from the École Polytechnique in France, a master's degree on applied mathematics, also from École Polytechnique, and a PhD on applied mathematics from the University of Paris-Saclay and École Polytechnique. He has held postdoctoral positions at the Laboratory of Mathematics of Orsay, and he has been a researcher, also as a postdoc, in a joint project of the Polytechnic Institute of Applied Sciences, IPSA, of INRIA Research Center at Saclay in Ile-de-France, and at Central Supélec Laboratory of Signal Systems. And currently, he is a researcher at INRIA at the Saclay Ile-de-France Research Center and part of the team Dynamical Interconnected Systems in Complex Environments. He's also a member of the Laboratory of Signals and Systems at Central Supélec. Professor Mazanti's main research interest is control theory, with several research topics lying between applied mathematics and engineering, such as stabilization of asymptotic behavior of time-delayed systems, control and stabilization of hyperbolic partial differential equations, mean field games, and switched systems. And today, he will present a talk with the title, The Multiplicity-Induced-Dominancy Property for Scalar Differential Equations with Time Delays. This being said, Professor Mazanti, the show is yours.
Thank you very much for this introduction. I would also like to thank for the invitation for speaking in this thematic day. And thank you everybody for being here. So do you see my screen?
Yes, we can see it clear.
Great. So I'll start my talk. So this talk will be about this interesting property called the multiplicity-induced property, multiplicity-induced-dominancy property for some kinds of time delay systems, which is a work I've been working on for a little bit more than 1 year with my colleagues, mostly of them at the same team as me at INEA. So during this talk, I'm going to start by an introduction, just presenting the problem and the kinds of things that are of interest to me. Then I'm going to talk a little bit more about the spectral analysis of time delay systems. And then I'm going to get a little bit more in the kernel of the talk, which is the multiplicity-induced-dominancy property. And then I'll finish with some examples of how this property can be useful. So contrary to the previous talks where nonlinear phenomena were a little bit more important, in this talk I'm going to concentrate on linear equations and on scalar equations with a single time delay, which can be then written in this form. So the nth derivative of y plus the nth derivative of y with delays, and here some constant coefficient. So for me, y is just a scalar valued function. My delay is just a positive number. I have some real coefficients here from a0 to an minus 1 and from alpha 0 until an. And this equation will be of retarded type if alpha n is equal to 0, because in that case, the highest order of derivation is only in the known delayed term here. And otherwise, it is a neutral equation. So I'm going to split the results. I'm going to talk between the retarded and the neutral case. Now, of course, when you see an equation like this, one of the main questions that you may ask about it is it stable? Is the zero solution stable? So can you compute if it's stable or not? Do you have an algorithm for determining stability in terms only of the coefficients of the system? That's one of the interesting questions. And the second one which comes with it is if you have some choice of some of these coefficients, let's say the alphas or maybe all of them, can you choose them in order to have a stable system? So these are two important questions from the point of view of analysis and engineering. And this is what I want to address in this talk. Now, my main motivation comes from control theory. So let's say that, for instance, I have some system which is described by a differential equation like this. So this is an equation with no delay of order n, but I have here some function u of t that I can choose. This is my control input. And I want to choose this control u in order to have a certain goal of the system. So for instance, to reach a certain target, or to choose this u in order to make the system stable. And so one of the most classical techniques for that is to choose this function u in the feedback form, that is choosing u as a function of y of t and some of its derivatives. And so the goal is to stabilize the system choosing this function u in this form. And when I do not have delays, this amounts essentially to modifying the coefficients that appear here in the derivatives of the system. And so if I can choose it, this amounts to saying that doing such a feedback is the same thing in a certain sense as choosing the coefficients of the system. But now, when you try to implement this in practice, in practical control systems, there's some delay because you have to acquire the measure of u, the measure of y, the measure of y prime, the measure of y double prime, and so on, and then compute u and then plug it into the system. And this gives us some delay. And so in general, we do not have this equation after we do the linear feedback stabilization, but we have some equation with delays like this retarded equation that I show here in this slide. So this is one of the motivations for considering these kinds of equations. And now, if you do not have delays, so if my equation is just all the roots are in the complex open left half plane or not. And then if I can choose these coefficients, given some n complex numbers here appearing complex conjugate pairs, I can choose these coefficients such that the roots of P are exactly the ones that I want repeated according to multiplicity. And I can do this by linear feedback stabilization with no delays, just by changing the values of my coefficients A here. So my main question is, can you do the same thing or similar things when we have delays? Now, when we have delays, we have this delay differential equation here, and now the characteristic function is given under this form. So you see that here we have still the polynomial part, and then another polynomial multiplied by an exponential that comes from the delay here. Now, for these kinds of functions, there are some classical facts that can be found in classical textbooks on time delay. So the first thing is that the roots of these characteristic functions determine the asymptotic behavior of the system in the space of continuous functions by saying that, for instance, we have exponential stability if and only if there is some negative spectral abscissa, that is, there is some positive number gamma such that all the real parts of the roots of this equation here are less than or equal to minus gamma. And another fact is that, except for the trivial situation where the delay is zero, this delta will have infinitely many roots in the complex plane. Now, the main difficulties when addressing the previous questions is that now we do not have a general algorithm like Routh-Hurwitz's criterion that can allow us to say where are the roots of delta if we know what are the values of the coefficients A, alpha, and the delay tau. Moreover, it is impossible to do a full pole placement because now we know that we have infinitely many roots and you can only choose finitely many coefficients. So you cannot place the roots of this function here anywhere in the complex plane. We have some constraints to respect when placing the roots of this function. So the idea is to try to do some kind of partial pole placement in which you choose some roots of this function here, and we try to choose these roots in such a way additional properties of this kind of characteristic function. This characteristic function is what is called a quasi-polynomial. So what is a quasi-polynomial? A quasi-polynomial is a function that can be written under this form here. So a quasi-polynomial is a function that can be written under this form here, where here my p's are non-zero polynomials, and here I have some exponential of some terms here with some different RKs, which can be positive or negative. I'm just assuming here that they are ordered. And there's this classical result by Colli and Szegő, which dates back from the 1920s, giving bounds on the number of roots of this quasi-polynomial in horizontal strips of the complex plane. So this number, there is this integer d, which is equal to n, which is the number of terms appearing in this sum minus 1, plus the sum of all the degrees of all the polynomials appearing here. And the number of roots of delta in an horizontal strip can be upper and lower bounded in terms of this degree d, of this number d here, in terms of the difference between the largest and the smallest r that appear here in these exponentials, and the size of the horizontal strip. So essentially, what this bound tells me is that if I have a large strip here, so if it's large enough so that this number here is greater than 1, greater than or equal to 1, then we have at least one root in the strip. And if it's small, so if this number here is small, then we have at most d roots in this small horizontal strip here. And in particular, in any horizontal line, we have at most d roots, and also in particular, the multiplicity of any root is at most z, because roots here are being counted with their multiplicity. So this integer d has been called in the literature the degree of the quasi-polynomial. And just to summarize the main results that we had so far, is that any root of delta has multiplicity at most d. And if we have a root which has multiplicity exactly equal to d, then there are no other roots in some horizontal strip around this root. Now, why are we bothering about these roots of multiplicity d here? And what is the link with the questions that I asked before? Because there is actually a link between roots of largest multiplicity d and dominant roots, that is, roots with largest real part, which is the property called multiplicity-induced dominancy. So there is this link between the roots that are the rightmost roots in the complex plane and roots with maximum multiplicity. Now, the multiplicity-induced property is shown to hold if whenever we have a root of maximum multiplicity, it is the dominant, so it is the rightmost one in the complex plane. And it has been shown to hold for many, but not all, families of quasi-polynomials, and so it can be applied to many families of delayed differential equations. Now, the usefulness of this property is that it can be used to stabilize systems with time delays. So, for instance, you can choose the free parameters of the system in order to guarantee the existence of a root of maximum multiplicity in the complex left half plane. And then the MIT property is going to say that this root of maximum multiplicity is necessarily dominant, and so we have exponential stability since it is in the left half plane. And now, how do we prove this multiplicity-induced dominancy property for a given system? Now, to impose that a root has maximum multiplicity is actually easy, because we can just impose it by saying that all derivatives are equal to 0 up to the necessary order. But proving dominance is the hard part. And this is usually done either by some useful factorization techniques or by applying some argument principle to show that there are no other roots to the right of the root with maximum multiplicity. So this link has been noticed in the literature since quite some time ago, in the 1950s, for some low-order cases. But it's essentially recently that this property has been developed and generalized to higher order situations and more systems. And so I've presented here some recent references with the kinds of systems that they treat. And I'm going to present you in a little bit more details in the sequel these 3 recent results here on the 3 most recent results that we have on which kinds of systems satisfy this multiplicity-induced property. So the first one is this one. So assume that I have this retarded differential equation here. So you see that this is of retarded type because in the delayed part here, I go only up to order n-1. The corresponding quasi-polynomial is this function here, and its degree is equal to 2n because I have one polynomial of degree n here, one polynomial of degree n-1 here, 2 terms here. So my total degree is n plus n-1 plus 2 minus 1, which gives me 2n. And the result that we have is that a given real number is a root of this maximum multiplicity 2n if and only if for every k, my coefficients are given by these horrible formulas here, which of course you can easily compute numerically when you need. And the interesting part of the result is that whenever I have a root of maximum multiplicity, it is dominant, so it is the rightmost one in the complex plane. All the others are to the left, and so this one determines the asymptotic behavior of my system. So how do we prove this kind of results? So first of all, of course, to simplify things a little bit, we can just do some translation and rescaling of the complex plane to get that it's sufficient to prove the result when the root is equal to 0 and my delay is equal to 1. And then there are 2 steps. The first one is to impose maximum multiplicity and find conditions on my coefficients. And it is a root of maximum multiplicity if and only if the function and its first 2n-1 derivatives are equal to 0, because we already know that the maximum multiplicity is 2n. And then this amounts to solving a linear system in these coefficients to get these horrible expressions here. And then how do we prove that it is dominant? Now, there's a very interesting property, is that when we have these conditions on the coefficients that are satisfied, we can factorize our quasi-polynomial delta as z to the power 2n, so it's a root which has been placed in 0 to the power of the maximum multiplicity, times some integral here that is an anonymorphic function of z. And it turns out that this integral is related to confluent hypergeometric functions, which is a class of special functions such that their integral representation can be given by this. And it turns out that the confluent hypergeometric function that appears in this factorization corresponds to a equal to n and b minus a minus 1 equal to n here. And this function has been studied previously in the literature, and it has been shown using some techniques from the study of the special functions that all its roots are in the open left half plane. So if I have a root of delta tilde, either it is 0 or it is a root of this confluent hypergeometric function. And so the rightmost root is the one that we have placed with maximum multiplicity, which is 0. And so it's the dominant root of delta tilde. Now, this was a result for placing roots, real roots of maximum multiplicity 2n. What you can also try to do is to place a complex conjugate pair of roots, each one of multiplicity n, and see what you can do if you can have the same kind of result also in this situation of complex conjugate roots. And the answer is yes, at least in the case n equal to 2, which has been chosen in this recent paper. So the idea is the following. In the case n equal to 2, if I place a real root of maximal multiplicity as 0, it will be a dominant root of multiplicity 4, meaning that all other roots of my quasi-polynomial will be in the open left complex half plane here. And so this one is the rightmost one. Now, we can show that if we place roots at sigma 0 plus or minus I theta 0, these roots are continuous with respect to theta 0. And so as I increase theta 0 from the origin, there are only two possible ways for us to have roots in the right half plane. It is if I had a root here in the left that was in the left when theta 0, 0, and that as theta 0 increases, it crosses to the right half plane, or if I had a root here, I have a root here that came from infinity, that is, as theta 0 tends to 0, this root tends to infinity. Using some classical bounds on the spectral of the system and studying roots in the imaginary axis, we can show that both situations are impossible. And so necessarily we have this multiplicity-induced-dominancy property also for complex conjugate roots. Now let me finish by talking a little bit about the neutral case. So in the neutral case, in our equation, you have this additional term here with the second derivative. And so since you have increased 1 degree of the quasi-polynomial here, the degree, 1 degree of the polynomial that appears here in the delayed term, the degree of delta also increases by 1 and is now equal to 5. And then there is this recent result that says that we have a root of maximum multiplicity equal to 5 if and only if these conditions are satisfied. And in this case, it is dominant. But actually, in the neutral case, there is a very also interesting property, is that when you place a root of maximum multiplicity, all other roots of the quasi-polynomial will be in the same vertical line. So they will also have the same real part as the root that we have placed in the real axis, which is not the case for the retarded case. So how do we prove this kind of result? So as before, we reduce to the cases 0 equal to 0 and tau equal to 1, and getting the conditions on the coefficients is the easy part. To prove dominancy, as before, we can also proceed by suitable factorization as z to the power 5 times some integral. This integral is still a confluent hypergeometric function, but as far as we know, there are no results on the location of the roots of this confluent hypergeometric function already available in the literature. So we had to proceed a little bit differently. And the idea here is that we first prove an a priori bound, saying that if I have a root of this, so if I have a root of delta tilde, which has not a 0 as a real part, then necessarily its imaginary part is bounded by pi, and this is done by some manipulations of this integral expression here. Now, once we get this a priori bound, we can prove dominance, because if we have a root such that the real part is different from 0, then necessarily it is not a root of z to the power 5, so it is a root of the integral. Being a root of the integral, these two integrals here corresponding to the real part and to the imaginary part are both 0. But if you see the one corresponding to the imaginary part here, this is actually a function that is strictly greater than 0 everywhere in 0, 1, and so it cannot be equal to 0, which gives us the contradiction. And this contradiction occurs because omega here is less than pi, saying that the function is positive. So necessarily, all the roots of this polynomial have real part 0. And then after we redo the translation, they have a real part as 0. So these are for the main results using multiplicity-induced dominancy. So how can we use them in practice from the point of view of control theory? So let's consider, for instance, that I have a control system given under this form. So it's a second order equation with some control term here. And I have some parameters zeta and omega here. Zeta is between 0 and 1, omega is positive. And if I do nothing to the system, it's already exponentially stable. And it has true complex conjugate roots with real part minus zeta times omega. But let's assume that For the system, I want to move a little bit faster than this. I want to go to 0 faster than minus zeta times omega. I can try to do a feedback control, but let's assume that you are in a situation in which you can measure y instantaneously, which is somehow quite reasonable in some practical applications, but not the velocity y prime, because measuring the velocity takes a little bit some more time. And so for y prime, we need some delay in order to be able to get the value of y prime. So let's assume that I choose a control which depends on the current position, on the velocity at some previous time, and on the position at the same previous time as the velocity. So if I do that, I have this quasi-polynomial here, which is the characteristic equation of my system with this control. And I can write down what are the conditions of having a root of maximum multiplicity at some S0, and writing down the conditions according to the conditions of the previous theorem for the retarded case. We have here a condition for S0, which implies in particular that it will necessarily be less than minus zeta times omega. So we can stabilize in a faster rate, and the faster rate actually depends on the delay. If the delay is small, we can stabilize much faster than the original system. So just to conclude, I'm just showing a small simulation. So in this case, I took zeta equal to 0.2, omega equal to 6. And you can see that when I have the control equal to 0, I have this complex conjugate pair of roots here. And then with a delay of 0.5 and imposing a root of maximum multiplicity equal to 4, I get this spectrum for my system. So you see that the dominant value here is the one that I chose, and this dominant value is smaller than the other one, meaning that when I stabilize my system, the closed loop solution converges to 0 much faster than the open loop solution, in which the behavior is given by these roots here. So that's what I wanted to say about this multiplicity-induced-dominancy property, and I'll thank you for your attention.
Thank you very much, Professor Guilherme Mazanti, for this wonderful talk. So I think now it's time to open the question and answer session. And for this, I will just ask the participants, the speakers, sorry, to habilitate their camera so we can all see each other. And so this being said, so far in the chat and in the YouTube, I don't see questions addressed to the audience, but now, well, I have my own questions, but before going to that, I would like to ask the ones that are connected if they have questions for one of the speakers. If such is the case, unmute yourself and address the question.
Johan, I have one question.
Please, Jaqueline.
Okay, I would like to know if for the model of Mackey-Glass, is there any version, Tibor, from involving state-dependent delays?
Well, of course, if you consider more complicated models, then it's possible to consider state-dependent delays. Of course,
yeah, but there are some studies about that.
We don't understand the constant delay case, so it's. But yes, there are models with state-dependent delays.
Oh, okay, okay. There are some studies about that then. So, okay. Thanks.
Okay, thank you. Any other questions from the audience? Well, let me just ask one question to see if there are some other shy participants that still don't have their questions. So the first question that I had, just to continue in the direction of Professor Mesquita, was regarding the Mackey-Glass differential equations. It came to my attention at the end when Professor Krisztin addressed the Ali effect, that you consider a nonlinearity of the form c squared divided by 1 plus c to the n. And my question is, what about other nonlinearities? What about, for example, if you consider a nonlinearity of the form c to the power m divided by 1 plus c to the power n? So two different exponents playing. Do you expect periodic orbits in this case? How do the conditions for the confining a contraction change? Do you expect chaos? What can you say in this direction?
Well, it's of course there are models even in that original paper by Michael Mackey and Leon Glass. They considered more nonlinearities, and that type of nonlinearity you mentioned, it's also interesting. And of course if you have one more parameter, you have one more freedom to create difficulties or more complicated dynamics. So it is expected that it's in some sense it's easier to prove complicated dynamics for those type of equations. You have an extra equilibrium point, and then it's we have results on that equation as well, proving connecting orbits between different periodic orbits, and also we have a homoclinic orbit, existence of homoclinic orbit, and other type of interesting dynamics for that equation with the Allais effect, not for the original Mackey-Glass equation.
Okay.
So it's I think it has a very rich dynamics, and we enjoy working on this nice equation.
Yes. Okay, thank you very much for your answer. I'm receiving in the chat a question. So Jan Sieber has a question for Odo Diekmann. I will ask just Jan Sieber to unmute and ask the question. Or if you prefer, you can send it through the chat. So Lenspec also has a question. They're sending it. Just a moment. Okay. So you cannot unmute yourself. Just send the questions through the chat, and I will just read them. There are questions for Odo Diekmann, from Lenspec and Jan Sieber. I'm just waiting for them to come into the chat. Well, in the meantime, when I'm just waiting for the questions to arrive, I had some other questions, and going back to the talk of Professor Mazanti. If I understood well from your theorem, the space of parameters for which you can certify stability, the set of parameters for which you can certify stability forms a thin subset of the space of all parameters. Is that right? You're the intersecting algebraic set given by your conditions, but there was a small non-algebraic part coming from the alpha parameters. Is that right?
Yes. Essentially, you have, for instance, the general theorem where you had the two n parameters. Essentially, they are all determined once you fix the S0. So you can see if the S0 is just a real parameter, then you have essentially a one parameter family in the space of all parameters where you can guarantee this maximum multiplicity. So we're currently working on seeing if we can get multiplicity less than the maximal, which would allow us to get a subspace with more degrees of freedom in the space of parameters. But the difficulty is guaranteeing that in this situation with less than the maximum multiplicity, you're still dominant. We know that this is true for some kinds of equations, but from some particular situations of lower order equations, but not yet in the general setting.
I see. Okay, Thank you very much. I had another question, but I'm going to read now. I had a question from Jen Siever to Professor Diekmann, which I'll read the question. The question is, the spaces in the twin setting are quite large. For convergence order of spectral methods, one needs higher regularity. And the question is, does one know that for typical renewal equations, periodic orbit are smooth in theta?
No, one doesn't know, because the regularizing effect in the case of renewal equations depends very much on the smoothness of the kernel. And so it depends on how smooth you are willing to take the kernel. So whereas for delay differential equations, if you have finite delay in every time step of the length of the delay, you gain one derivative. And that doesn't hold in general for renewal equations. And actually, this is really a subject where more work is needed for renewal equations, to study the smoothing properties of renewal equations. This is a largely open question, I think. There are some quite old papers on the regularity of a convolution product depending on assumptions concerning the kernel, but they are not easily taken in this step-by-step way as we do for delay differential equations. So this is really an open area.
Okay, interesting. An open question in this direction. Okay, I have another comment from Len Speck, another question from Len Speck to Professor Otto Diekmann. I read the question, and the question says, you showed that the twin semigroup as a theoretical framework and pseudospectral approximation as a numerical framework for delay equations. My question is, can we use the twin semigroups to show more properties for the pseudospectral approximation, convergence, etc.? If so, what key aspects from the twin semigroup make this possible?
Well, this is an interesting question because it again points to an open area, I would say. Because one of the dreams I have, but it's really wishful thinking and no results or indication whatsoever. But you see, if you take like a state-dependent delay equation and you do the pseudospectral approximation, this smoothness difficulty disappears completely because these polynomials are infinitely smooth. And so this difficulty that you have for state-dependent delay isn't anymore there in the pseudospectral approximation. Now, if you could prove that taking the limit where, say, the number, so the mesh size goes to 0, so the number of points goes to infinity, if you somehow could pass to the limit and derive properties for state-dependent delay equations like center manifold theorems or bifurcation formula for this higher codimension bifurcation, all that kind of thing. By passing to the limit, taking the ODE results and showing that there is a meaningful limit when the order of the approximation goes to infinity, that really tells you something about the original state-dependent delay equation, that would be wonderful. And then, of course, the topology that you take in the state space matters. And I still think that this somewhat weak topology where you just take inner product or products, I should say, not pairings of elements of this space Y diamond with the original space Y, should hopefully give more opportunity to prove convergence than when you have norm estimates. So there is hope, but it's open, completely
it's a difficult
open.
Question. Yeah. Okay. Thank you very much, Professor Diekmann, for your answer. I have a small question for Professor Mesquita. It attracted my attention, the manifold that you mentioned, XG2 star. this stable closed manifold. And my question is the topology of this manifold relevant for your problem? Or can you say something about the topology of this manifold that you intersect with the cone to get your solutions?
Actually, the X to G star is not longer a manifold because of the regularity, but the X to G is a manifold, and X to G star is a closed subset of the X to G. And we like that type of set because we have the invariance of that. So when we apply that argy about the cone, we are still in that X to G star, and then we can repeat this process. But the main thing about the X to G star is about the invariance of we have from that. And we use that to construct the other manifold, that's the M3, that if we intersect this X to G star with C3, then we have the manifold. Yeah.
I see. So the topology is not there playing a role. Well, I just check one moment more, but I think, well, no more questions in the chat or in the YouTube channel. I'm given a last opportunity for one moment. Oh, I just get a question from Sebastian Janssen. And this is a question for both Professor Diekmann and Professor Mesquita. And I read the question. The question is, would you think that twin semigroups help to study delay equations with constant delays but non-smooth right-hand sides, such as measure delay equations and/or delay equations with impulses?
If Diekmann would want to start, I can complement.
I haven't really thought about it at all. So my answer is I don't know.
Yeah.
Okay,
yeah.
good.
The same. I don't know, actually. It could work. I don't know. I really don't know. Yeah, it's a good question. Yeah. Because the main thing that you have from that type of equations, like measure equations, you do not have a continuity of the solutions. You can have that your solutions has bad behavior. So yeah, I don't know.
Okay.
It's something to think.
Okay, so it seems that there are no further questions in the chat or in the YouTube channel. So let me just utter some last words to thank all the speakers for their time, dedication, and sharing all this wonderful mathematics with us and with the rest of the world. And again, to the organizers and the institutions funding this activity, thank you very much. And so I think with this, oh, Jaqueline is saying you want a picture?
Yeah, with the speakers and yeah.
Okay, so you want the speakers to stay at the end and then we take a picture of the...
Okay, great, yeah. Only to
okay. So thank you very much for attending this, for the rest of the audience, and then we will just stay with the speakers to take a picture. And so this is the end of this